Hello, and welcome to the lesson on catalyst activation energy and temperature. I decided to do this lesson instead of the other one on the second one on mechanisms, which is much more difficult. And you can see I have a helper. Where is he? Helper! So here's my helper who's helping me make the video today. Say hi, he's sleeping. Say hi, helper. Hi! Okay. Back to sleep, Kaiser. Alright. So. Hold on one second. Alright, now the camera is away. So, catalysts, we're going to talk about things that catalysts do. So one of the things that the first thing is they speed up the rate of the forward reaction, okay? And they do so by lowering the activation energy. And we're going to talk about how catalysts do that, okay? And one of the ways that they do that, which we're going to look at, is they provide a different mechanism for the reaction. Now, they also, as fast as they speed up the forward reaction, they also speed up the reverse reaction. So that was when we were saying that catalysts have no effect on equilibrium because they affect both the forward and reverse reaction equally. Catalysts also are not used up by the reaction. They can catalyze the same reaction over and over again. Enzymes, which a lot of you learned in bio, are an example of a catalyst that we learned. And catalysts, which we're going to see, help the formation of intermediates. They lower the barrier, energy barrier, or the activation energy needed to get to the intermediate, which is in that valley, if you remember, of the energy diagram. Okay. So this is an energy diagram, and we see the black energy diagram is the diagram without the catalyst, and the red diagram is the energy diagram with the catalyst. And if you look what the catalyst affects, okay, it affects the path of the reaction. So if you notice all these humps, okay, that are in this energy diagram, the catalyst is changing the mechanism of the action. And by doing so, making the mechanism easier or require less energy. So therefore, the activation energy is lower, or the distance between the top hump is lower. So if we look at the size of the black arrow with no catalyst, the activation energy here is greater than with the catalyst, which is the red arrow. Okay. Now, another thing that catalysts do not change, okay, so far they change the activation energy, and they also change the pathway of the reaction, or the mechanism of the reaction, designated by these different humps. If you look at here, but the other thing that it does not change is delta H. Okay, so on this graph, delta H is always the difference of the energy of the reactants minus the difference of the energy of the products. So if we're trying to sort of see where this is on this graph, as I try to get the pen out, the distance between X and Y and Z here, this is delta H. And you'll notice that the enzyme, or the catalyst, sorry, I'm saying enzymes, does not change delta H. Delta H stays the same. So, in terms of summarizing what catalysts do and do not do, okay, they increase K because they're increasing the rate of the reaction, so they increase K, okay, and they do so by lowering the activation energy, okay, making that barrier easier to be overcome, okay. And they also provide an alternative mechanism, which as a result requires less energy to occur. Okay. Now what catalysts don't do, okay, is that they don't affect equilibrium, because they affect both the forward and reverse reaction equally, okay, and they don't change delta H or delta G, okay. So delta H is going to stay the same, and enzymes or catalysts can't make reactions occur that wouldn't. So reactions that have positive delta Gs are not going to occur with a catalyst if they wouldn't occur without a catalyst. Okay, so catalysts do not affect delta H or delta G. They only can make reactions that would occur faster. So here we have our classic energy diagram. And one of the things I want to make sure that I brought up the point is what an activated complex is. So the activated complex, which is just about when the products, so when these are about to turn into water, okay, so these bonds are just about to form, the bonds between H and O are just about to form, okay, is at the top of the activation energy, okay? And what catalysts do is they lower this hump so it's easier to get to the activated complex. And they do that by changing the mechanism, making the mechanism require less energy, and making the orientation of the collisions either easier to occur so it doesn't take as much time for that correct orientation to occur. Okay. So an example of a catalyst that, like, we talked about enzymes, and but an example of a catalyst that works in cars and catalytic converters, actually. So if you know anything about catalytic converters, you may know about this, is platinum. Okay, so when your car is running, it produces some carbon monoxide, and carbon monoxide is dangerous. So cars have catalytic converters that help the carbon monoxide react with oxygen, okay, to produce a less poisonous gas, which is carbon dioxide. Okay, now, in cars, they either have a platinum or palladium catalyst. Okay, let's take a look at how the catalyst helps this reaction. So, if we take a look here, we have oxygen, all the white atoms, and carbon are the green atoms. And the oxygen atoms are attracted to the platinum surface. And when they're attracted to the platinum surface, the platinum helps break the bond between the oxygen atoms. Okay? Now, also attracted to the platinum surface are the carbon dioxide molecules, carbon monoxide molecules. And because these oxygen molecules are here, and the carbon monoxide molecules here, they're more likely to collide, or it's easier for them to collide. And if you see they're about to collide here, this is the activated complex when they're about to collide, and then they produce carbon dioxide, which is actually not attracted to the carbon dioxide, so it gets released from the catalyst surface. Okay? So here's another image of this. So if we take a look at what the text says, it says both oxygen and carbon monoxide molecules bind to the metal atoms on the surface of the catalytic converter. So here is the platinum. That binding of the platinum strains and breaks the bonds holding the oxygen molecules so they can break apart. And then the oxygen molecules are free to collide with the carbon monoxide, which is also attracted to the platinum surface, to form carbon dioxide, which is not attracted to platinum, so it's released. And then this can repeat and repeat. Without catalytic converters, cars would cause a buildup of poisonous carbon monoxide, which obviously is not good for humans. So again, what platinum does, right, is it helps break this bond between oxygen, so that makes that require less energy, and it makes oxygen more likely to collide with CO to make CO2, thus lowering the activation energy. So, on one of the video lessons that we did, you looked at mechanisms, okay? And the AP exam likes you to look at a mechanism and identify what the catalyst is in the mechanisms, okay? And they get confused with intermediates, okay? So catalysts are present as reactants in the beginning and also at the very end of the reaction. Unlike intermediates, which are produced in one of the initial steps, but then consumed. So if we take a look at this mechanism for making, turning ozone into oxygen gas, ozone, O3 is ozone. If we take a look, let's try to first identify intermediates. So intermediates are ones that are present in this first step of the initial reaction. So as we see in the first step, this here is produced, and in the second step, it's used. So ClO is the intermediate. Now, catalysts are things that are present at the reactants in the very beginning and also at the products at the end of the mechanism. So if we see a look at this, if we can see, is there anything that's in the reactants that also present in the products, and we have chlorine. So chlorine is present in the reactants, and it's also present in the products. And remember, catalysts are not used up by the reaction. So in this case, Cl is acting as a catalyst to speed up the reaction. It's present in the beginning, and also present at the end. It's not used. Okay, the last thing we gotta talk about is temperature, and temperature's effect on K and activation energy. Okay, so like catalysts, temperatures increase K, meaning they increase the reaction rate, but they do not affect activation energy. So the question is, how do they increase K, but they don't affect the activation energy? So if we remember this Boltzmann distribution curve when we were learning about gases. When the temperature so this graph has speed or energy on the x-axis and the number of molecules with that speed or energy. And when we increase the temperature, we remember that the curve shifts to the right because there are more molecules now at higher speeds because the temperature is higher. Okay, but the overall size of the curve drops because the number of molecules need to remain the same. Okay, now, let's say, remember on this axis is energy. Right here is the amount of energy needed, okay? So on this x-axis to overcome the activation energy. If you notice the red graph, which is at a higher temperature, more molecules, okay, are past the activation energy, and therefore will have enough energy to react. Whereas the ones that are colder, less molecules are past the activation energy, so less molecules will be at the energy needed to react. So what temperature does is because molecules are moving faster, it makes molecules have more energy, and therefore more of them are more likely to overcome the energy barrier created by the activation energy. That I would write down. Okay, so I'll say it again. So because when temperature increases, more molecules have higher kinetic energy, more of them are likely to overcome the energy barrier, or the activation energy, needed to do the reaction. So if we take a look at, these are some like questions about energy diagrams that we're going to go through. So if we take a look at the difference between these two graphs, here, this dotted line represents the amount of energy needed to do the reaction, okay? And that line has been moved to the left, or the amount of energy has been decreased. That can only be done, activation energy is only changed by a catalyst, okay? So nothing else changes activation energy but catalysts. So B, which has the energy needed for the reaction reduced, because the line is more to the left, okay, that can only be done by a catalyst. If we look at this, what responds to the activation energy? The activation energy is always the distance from the reactants to the top of the hump. So in this case, this is line 2. Okay. At what point on the potential energy diagram does the activated complex, aka transition state, occurs? That occurs at the top of the hump. So 3 is where the activated complex is, so the top of the activation energy. How many steps are involved in this reaction mechanism for the reaction indicated by the energy diagram below? So the number of humps tells you the number of steps, or the number of activation energies. So this energy diagram has 2 humps, therefore it requires 2 steps. Also remember that the intermediate is in the valley between the activation energies. Okay. Addition of a catalyst that speeds the forward reaction will also speed the reverse reaction. We said in the beginning of this lesson that that's true. Therefore, catalysts do not affect equilibrium. They affect the forward and reverse reaction equally. For this question, how many reaction intermediates are involved in the diagram indicated by the energy diagram? So that occurs whenever there's a valley. So there's a valley here, which is an intermediate. So there's one valley here, and there's another intermediate here, which also counts. Now this one is not an intermediate. Here are at products, because there's no more sort of, the energy diagram ends. So this mechanism here has 3 steps and 2 intermediates. Notice also that this one here, the slow step is in the beginning, because it has the largest activation energy, and slow steps have the largest activation energy. That's why they occur slowly. The energy diagram indicates that the second elementary step in the rate reaction is the rate determining step. That is false. And the reason why that is false is the second hump, or the second activation energy, is lower. So that is the fast reaction. The lower the hump, the lower the activation energy, the faster the reaction can occur. And then last but not least, this is always the hard one. So it asks this overreaction. So we have reactants versus products, right? And here the reactants have more energy from the products. So that means energy was released, okay? And when energy is released, that means the reaction is exothermic, okay? So that eliminates 4, 5, 6, okay? Now, the energy released is always the difference, or the energy absorbed, is the distance between the reactants and the products, which on this line is dedicated by line F, okay? So that means that this reaction is exothermic, because energy is released, the reactants have more energy than the products, okay? And energy is released when a reaction is exothermic, and the distance, or how would you calculate H would be the distance from F, from reactants to products, which is given by F. Alright, this is the last video lesson for a while, I hope. Alright, go answer the questions.